Hello and welcome to another video. In this video we're going to be continuing on with the TypeScript line 75 and we're going to be doing alien dictionary. And this is probably the hardest problem we've done so far, other than maybe the word break 2, whichever one, or the word search 2. This is pretty close to up there. So in this problem, there's an alien language that uses the English alphabet, however the order of the letters is unknown to you. You're given a list of words from the language's dictionary. Note that it is claimed that the strings are sorted lexicographically by the rules of this new language. If this claim is incorrect, return empty string. Otherwise, return a string of the unique letters of the alien language sorted in lexicographically increasing order. So first of all, it even takes a while to understand what they're saying and exactly how you would do some of this. But essentially, what they are saying is, given a list of strings, give some kind of alphabet ordering that would make this list of strings valid, sorted from left to right. So let's take a look at this first example. So here we have WRT and WRF. So the two letters that differ are T and F. So T has to come first in the alphabet, and you can see it does in this output. Now let's compare these next two words. So we have WRF and ER. So W has to come before E, right? So essentially, whenever you compare the two words next to each other to see if they are sorted, you need to see what's the first differing letter and does that letter come first. So here, W does come before E. Then in this thing right here, the two letters that are different are R and T, so R has to come first. Then you have E and R, so E has to come first. So this is fine. Now for Z and X, obviously Z just has to come first. Now for this, there is no solution because you can't have ZXZ. That would be like saying ABA is sorted. It's obviously not, right? You can't have Z come before X and after X. So this is invalid. So the first thing we're going to do, and this is going to make our code a lot easier, is we're just going to go through all the words and we're going to get a list of or a set of all the unique characters in here. And essentially, I'm going to kind of so first we're going to do that. So let's just say we go through all the words. So we go through, let's take this first example. We get all the unique characters. And then what we're going to do, so we're going to represent this as a graph. So for every character that comes before another character, we're going to create a dependency, right? So for example, when we look at these two words, since T comes before F in this example, we're going to say there's going to be an edge from T to F, meaning that there's a dependency here, right? You have to go to T before you go to F. So that's what we're going to do. For every node that there's a difference, we're going to make an edge. So when we instead of creating a set of characters, we're actually going to create a hash map. And then every new character, we're just going to initialize a default. We're going to initialize a default structure to. Because in TypeScript, you have to be checking if things are in all the time, and we're going to make that easier by just literally taking every character and adding it to the hash map in the beginning, so we don't have to keep checking is this in the hash map, is this in the hash map, did we initialize it yet? So essentially we're going to have two things for every element. So let's say we have the character W. We're going to have two things for this character. We're going to have a set, and you can have an array as well. We're going to have a set of every character that it has an edge to, kind of like an adjacency list, right? You can build an adjacency list by having a key and then an array for values, or a set as values. Those are typically the most common things. And basically what I want to be doing is I don't want to be creating multiple edges because they're kind of redundant, right? If there's an edge from W to T, that means W has to come before T, but we don't need more than one, right? What's the point? So that's what we're going to use a set. And it's going to be a little bit faster for checking if things are in there. So we're going to have a set for everything, and we're also going to have one more value, and that value is going to represent the number of edges that have to come before this edge. So initially, we're going to have an empty set and 0, right? Which means that there are no nodes that W actually has an edge to, and W has no dependency. So essentially, this is the dependencies your letter has. This is the number of letters that have to come before this letter. So let's kind of walk through this, and let's draw out our dependencies, essentially. So we're going to have how many letters we're going to have. So initially, like I said, we're going to go through every letter, and we're just going to make it all equal to this. And then we're going to change dependencies as we go. So we're going to have 5 letters, so we're going to have 5 of these. And then we can also draw it out as a graph as well. So essentially, you're going to have 5 of these. So 1, 2, 3, running out of space here. Actually, instead of this, let's actually just draw the graph first. So just imagine we're going to have this for every single letter, and then let's draw the graph, right? So the graph is just going to represent this list of edges. So we're not going to draw out this because this is going to be a lot of letters. So instead, let's just draw the graph. But essentially, for every letter, we will add it into that, and let's kind of walk through what would happen. Okay. So we're going to compare word by word, and imagine you have all these nodes. So let's say you have all these nodes to start off. So you have, let's take a look. So we have W. Let's actually maybe even write this out so when we have more space, right? So let's just say we have WRT, WRF, ER, ETT, R, FTT. Okay. So first thing, we're going to draw out the nodes, and that's just going to represent new entries into the adjacency list with the set and dependencies. So we're going to have W, we are going to have R, we are going to have T, and we're going to have F, and finally, what's the last letter? E? Yeah. So this is gonna be like our start, right? Where like every single one of these is in our adjacency list, where we have the set and the number of dependencies. And now let's walk through these. So we're going to be comparing letter by letter for each two adjacent words. So we're going to be comparing these two adjacent words and these two adjacent words and so on, right? That's how you compare to see things are sorted, right? You just compare things that are side by side. So we're going to compare these two W's. Well, these are the same. So that means we have to keep going and compare more letters, right? So let's compare these two letters. These are the same. So then we have to keep going. Now we have to compare these two letters. So these are different. So T has to come before F. So T is going to have an edge to F. And this is similarly like, let's say you have a word like ABC in English, right? And then you have a word like ABD. ABC has to come first because these two are the same, but C has to come before D. So that's kind of like the same intuition here. When the letters are the same, you have to keep checking further down to see like which one comes first, right? But if they're different, like if you compare ABC to DEF, you don't need to compare anything other than the first letter. You know, like, well, ABC has to come first because A is smaller. So similarly, the same logic here. Okay. So now we need to compare these two words. So the W and E are different, so there has to be an edge from the W to an E. So edge over here. Now we are going to compare the next. So E, R, and ETT, E's are the same, but there has to be an edge from R to T. So let's draw that. Okay, and now we have ETT and RF to T. So E has to have an edge to R, so that's going to look like this. And there we go. So essentially, this is our graph, right? We have, this is what it's going to look like. And basically, from every single word, you're going to have like one more edge maximum. There are a few edge cases that I'll also talk about, but let's get into this. So essentially, the way this looks is we're going to be using a topological sort algorithm. And basically what a topological sort algorithm does is it takes all of the edges or all of the nodes that have no dependencies, right? So if we take a look, dependency means there's an edge going into it. So W has no dependencies. And so essentially we're going to represent this graph as an object, but this is kind of what it's doing. So we can actually just write how many dependencies there are, right? So for W, there are 0. For T, there's 1. For E, there's 1. For F, there's 1. And for R, there's 1, it looks like, right? How many edges are going into the letter. So that's how we're going to represent it, right? So essentially, every edge we're going to represent in the set. So like for W, in the set of edges coming from W, we will have E, right, and so on. So this is going to be how it's represented. And then for the dependencies, this is what it looks like. So when we're making this result, we're just going to be taking characters, and it doesn't really matter the order, right? Any character with no dependencies can go into the result in any order, meaning those characters like aren't checked here, so those are fine. In this case, there's only one, but there's going to be times where you're going to have multiple characters that the order doesn't matter. Okay. And a really easy example of that, I guess, is like, let's say your array is something like maybe like this, rack, let's say. And then your other word is like, now obviously this is the alien one, not the English. Let's say it's like this, and then this can be any number of letters, right? So anything after the M, because there's only a dependency from C to M, right? Anything after this M can be whatever. This can be like D, as long as they aren't in any of them, it could be like D, Z, X, whatever. Like, these don't really matter. Because these can be, like, the order of these characters doesn't matter at all. Okay. Because, and the reason why is because no matter what these characters are, as long as C comes before M, this can be anything, and it will, and this word will still come first. And I guess while we're here, we can look at the other like edge case. So let's say we have something like this. Let's say we have rack, and then we have something like this. Yeah, RAC. So this would be a problem, and this should never, like, we can just return false straight away. So if while you're comparing, if the word on the left runs out before the word on the right, then this is going to be a problem, right? Because just like in English, let's say you have like ace, and then you have like aces, and aces comes first. That wouldn't make any sense, right? A should come before aces, because a blank letter, like the end of a word, should always come before another letter. So similarly here, this would be invalid. So the same thing here. So while you're comparing characters, if you're at a character here and you're out of bounds here, then you can just return false straight away, and that's going to be like an edge case that is kind of hard to find. But yeah, so essentially what we're going to have in our result here, going back up to this example, is we're going to take the letters with no dependencies. The word doesn't matter. So let's just say we take, okay, we'll add W. Now that you can think of W being like a prerequisite for all the letters that has an edge to. So W has to come before E, but now that we already have W, now we can get rid of this edge. And now E has no edges coming to it. So now we can add E. Now E is a prerequisite for R, so we can get rid of that edge. Now R has no edges coming to it, so we can have R, and then T has no edges coming to it, so we can have 0 here, we can have T, and then finally F will have no edges coming to it, and I'll have this. And I believe this was a solution, right? WERTF, yeah, that's what it is. And like I said, you are going to have a lot of scenarios where the order of the letters doesn't matter, and what that would look like is, let's say you had the same graph, but you had, your edges were like this, and even, you know, yeah, something like this. Let's say your edges are like this. Now, E, F, and W have no dependencies, and these do. So E, F, and W can be written in any order. It doesn't matter. Now, let's look at a case where this won't be valid. So essentially, the cases that it's not valid is any case with a cycle. So for example, if I have something like this, let's actually draw an easy one. Like, let's do this. Like, every edge just has an edge to the left. So this is the case. So now the problem is everything has one dependency, right? Everything has one dependency. So you can't like pick a starting edge. You can't or starting node, because everything has dependency. So you can't pick anything. Or you will just like have some stuff, but then you will run into loops later on. But essentially, anything that has a cycle will never work. So that's kind of like this Kahn's topological sort. It's like a good cycle detection thing, because it'll essentially, you will just keep getting rid of nodes with no edges. But we might run into nodes, like after a while, we might just have nodes that all have edges, and there's nothing we can do, right? Another example would be like, let's say we have something like this. So like this is fine, but then we have 3 letters that have a cycle here, and so on, right? Like there's a bunch of examples of this, but essentially what we're going to be doing is we're going to be getting rid of nodes with no edges, and then we're going to be getting rid of their edges, and then we're going to check at the very end, like, did we use every letter? And the way we're going to check, did we use every letter, and that's why I said we're going to do this ahead of time, is we created this adjacency list by going through every single letter and every single word preemptively. So we're going to have like some keys in our adjacency list, right? We're going to have like a number of keys here, and we're just going to check, like, is the length of our result the length of the keys? And then if it is, we've used every letter. And also you need to have some kind of mechanism for in your result to make sure you don't have like duplicate letters, right? You shouldn't really be able to get duplicate letters, I think. Like it should never happen. Yeah, so I think looking back, I don't think you need I think you're never going to get duplicate letters with this algorithm actually. So I think it'll be fine. So I think I can modify my code to make it a little bit simpler there. But essentially, that's kind of like going back over. That's like pretty much what we're going to have. So we're going to go through every single letter and every single word. Instead of adding them to a set, we're just going to add every single letter to a hash map, and then that letter will have value, a set, and a number of dependencies. And then we're just going to go through the keys, take everything with no dependencies, add it to some kind of like. So with this const topological sort, you can just have a stack of like all your available letters that have no dependencies, and then you can just be popping the letters, and then every time you pop a letter, you just get rid of nodes. You just get rid of edges from it, and then every time a node has no more edges from it, then you add it to the stack. So let's kind of walk through what that would look like as well for this really fast, and then we can look at the code. So let's say we have these like edges, right? I'm not going to draw the number of dependencies. I'm just going to draw the edges. So essentially what would happen is, so we have a edge from T to F, right? We have an edge from E to R. I'm sorry, we have an edge from, not T to F, we have an edge from W to E. So let's draw that. We have an edge from R to T. And then we have an edge from E to R, I think. Something like that. So essentially our stack is going to first have all of the nodes with no dependencies. So that's just going to be W. And then we're going to be popping from a stack. So let's say we pop W. As we pop from W and get rid of edges, we will check every node that we get an edge from. We got rid of an edge, like does it have no dependencies now? And if it does, let's add it to the stack. So we're going to say, okay, so now that we got rid of this edge, E has no edges, let's add it to the stack. And then we're going to pop E, get rid of this, add it to the stack, and so on and so on and so on, until your stack is empty because the stack represents edges with no dependency. And then once our stack is empty, then we can just check how long as a result did we use every single key. And that's pretty much going to be it. So it is a lot of code, and there are a lot of edge cases, and it's kind of tricky in TypeScript, so let's go through it. And I actually have it written down with comments just because I don't want to have like a 40-minute video. So let's go through all the code, and then we can see if we could optimize it further. So we're going to have this letters adjacency list, right, where it's going to be an array of a set of strings, meaning there's an edge from this string from this node to another node. It's going to have a set of all the nodes that it has an edge to, and the number is going to be the number of dependencies that this letter has. So we go through every letter, and we just check if it's not in our hash map. Let's just initialize it to a new set of nothing and no dependencies. Then we need to actually go through all of the words and compare every word to the word. So in my case, I just compare every word to the word after it, character by character, right? And so this is the case where, like I said, if J is greater than words I length, meaning you have a word like this, right? You have like A, B, C, and then A, B. So essentially what would happen is A and B would be equal. You would be C here, and then this would be empty. So this can never happen, so we can just return straight away. Then we get our two letters, our first letter and our second letter. These are the letters we're comparing. If they're equal, let's just go to the next letter, right? Similarly, if we have like A, B, D, and A, B, C, if we're on A, we'll compare, and if they're the same, let's just keep going, right? And then we're looking for the first different letter. So this is the case where we've already seen this edge before. So let's say we have like A, B, C, and then A, B, D. So essentially, you would have an edge from C to D, but we've already seen it before. Then we don't need to really do anything. We're not going to add another edge and a dependency, right? Because we're using a set. So we don't need multiple, like, we already have this dependency. So if we have this dependency, we can just break as well, and we don't need to keep checking more characters because we already found a different character. Otherwise, we're going to add the second letter to the set from the first letter, and we're also going to increment the number of dependencies for that second letter, right? So if we had, once again, A, B, C, A, B, D, for the letter C, we're going to add D to one of the nodes that it has an edge to, and then for D, we're going to add one to its dependency. So if it had 0, now it has another one because it's dependent on C now. And then basically, as long as the characters aren't the same, we can just break immediately, right? So if the characters are the same, we're going to continue to the next part of the loop. Otherwise, we can break because we found a different character. So now we have a result, and we have uniques as well. And our result is basically going to be just an array of characters that we're popping. And then uniques is going to make sure that our result has different characters every time. But like I said, I don't think we need this. So we're actually going to get rid of this and try to... so we're going to get rid of this set because I don't think we need it. So we're going to get rid of this. And then essentially what we're doing is we are going through our initial hash map, and we are checking everything with no predecessors. We're going to add it to a veil, right? Anything that has no dependencies, we're going to add it to our stack. So a veil is just basically our stack of available letters. And then while it has a stack, we can pop a letter. So like I said, I think we can get rid of this because we shouldn't really have duplicates here. So I don't think you can get this multiple times. So we should be able just to get rid of that, get rid of this. And yeah, so we pop our letter from our stack, we add it to our result we're going to be returning. And then what we need to do is we need to check what are all of its successors, right? And for every successor, we're going to decrement its number of dependencies. And then if it has 0 dependencies, then we're going to push it to our stack. And then finally, we need to check, did we use every letter? And the way we check if we used every letter is, remember, if we go back up here, we actually made a object of all the letters, and we went through every single word, and for every single new letter, we made a key. So we're just going to check, is the length of our result equal to the number of keys we have in our keys? If yes, let's return it. If not, let's just return an empty string because we haven't used all of our letters. So let's try to run that. And like I said, I don't think we need the set. I think, thinking about it again, I don't think we need it. I don't think you can ever run into the same character. Yeah, you can't. Okay. And this is all over the place as always, so, you know, it's like a good solution. And so the nice thing is here, as we're going to look at the time and space, a lot of this time and space, I would argue, is going to be basically 0. So let's kind of walk through it. So for this letters, if you think about it, because this is only lowercase English letters, this is only 26 letters, right? 26 letters, and then how many edges can you have from every letter? Well, only 26. And how many dependencies can you have? Only 26. So even though this can be like, 500 total letters or something, I would argue that this letters is going to be O of 1 space, but we'll get into that. But essentially, this is the part that is actually the bulk of our time. So we do have to go through every word, and then we have to look at every character of every word. So let's just call that like O of W, where W is all of the characters in every word combined. Right. Then we have to compare characters. And once again, worst case scenario, imagine all our words are like ABC, 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 right? Like this. You would basically have to compare every word to every word next to it, and you have to compare every single character. So that would be O of W, because essentially every word would have 2 comparisons, except for this one and this one. Every word would compare to the one to the left and the one to the right. So that's O of W. And yeah, and like this is all constant time, so that's O of W. Now this part is the part that I'm going to argue is going to be all O of 1. So essentially, when we go through our letters, because we only have 26 letters, I would say this is O of 1. And then I would also argue that this actual topological sort itself is O of 1, because we're going through our letters and we're getting rid of nodes. But if you only have 26 letters, you can only have like 26 letters, and then each one can have an edge to like every other letter or something, right? So it's 26 and 26. So I'd argue this whole while loop is basically O of 1 because we only have 26 letters. Now, if they did say that like the letters were like any ASCII value or something, whatever, then this wouldn't be the case. But I would argue that this is O of 1, and yeah, this is all O of 1 as well. So essentially, our big time like problem is this part here and this part here, where we're going through every word and comparing it to every other word, because that can be like bigger numbers, right? So, but as far as the characters, I would say 26, 26. If you want to get fancy and you want to like, you don't want to simplify those to O of 1, then you can figure out what those would be. It wouldn't be super difficult, right? It would be something like you basically use nodes and edges there for a graph. But I'm just going to say it's O of W here, and for the space, I'm actually going to argue that it is O of 1 space, because if we look at all the things we make, For letters, once again, only 26 letters, and then every letter can only have 25 edges, and this can only be 25, so it's all limited no matter how big your word is. Your word can be a billion characters. This will still only get, only 26 letters. So I would argue that that is, constant space there. And then I think that's most, this result can only be 26 letters. This available letters can only be 26 letters. This is all, So pretty much all these things that we make can only be 26 letters, and therefore I'm going to say it's O1. And yeah, it's actually going to be it for this problem. So quite a long one, as you can see, a lot of code, a lot of comments. But yeah, definitely a good one to do, and probably one of the toughest problems we've done so far. So even if you've seen the solution, I would definitely recommend redoing it. Make sure you can handle a lot of the edge cases, because there are a lot, and this is really good TypeScript practice, because you do have to make, I guess I didn't even show this part here. So for our letters, our type of our letters is actually an object of type string, and then the value is actually a tuple of a set that takes a string and a number. This part is also kind of tricky, right? So there's a lot of these things that you get to practice in TypeScript for this problem that you can get a lot of errors with. So definitely would recommend you to do that. And yeah, it's going to be all for this video. So if you liked it, please like it, and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.